Lesson 8.2, Properties of Logarithms, Part 1, Expanding. In these next two lessons, students will be able to expand and condense logarithms using log properties. Take a moment, pause here, play when you're ready, evaluate these 5 logarithms. Alright, hopefully these weren't too challenging for you. Log base 2 of 2, 2 to what power gives you 2? That's going to be 1. Log base 2 of 4, that's going to be 2, and then 3, 4, 5. I want to use these logarithms to illustrate a point about how we combine logarithms together. Consider this question right here, log base 2 of 2 plus log base 2 of 4. Take a moment, evaluate this expression. Log base 2 of 2 is 1, plus log base 2 of 4 is 2, and 1 plus 2 is, of course, 3. But if you take a moment and think about this, 3 is really log base 2 of 8. So what we could have said is log base 2 of 2 plus log base 2 of 4 is actually log base 2 of 8. Now look at that equation there and think to yourself, how could I have gotten that answer, log base 2 of 8, without actually adding something together? And if you look closely, you'll recognize 2 and 4, the inputs of the logarithms, multiply to give you 8. That's interesting. Let's look at another example. Log base 2 of 32 minus log base 2 of 8. Think about this one for a moment. Now hopefully you recognize log base 2 of 32, that's 5, minus log base 2 of 8, that's 3. 5 minus 3 is, of course, 2. And 2 is log base 2 of 4. So in this case, 32 and 8, how do those combine to give you 4? We didn't subtract 32 minus 8. We didn't multiply 32 times 8 like we did on the last one. On this one, what we actually did is 32 divided by 8. So when I'm adding logarithms together, you can actually multiply the inputs of those logarithms. When I'm subtracting, I can divide. Multiplication is to addition, as division is to subtraction. Let's look at one more example before we summarize these rules. 2 log base 2 of 4. Well, log base 2 of 4 is itself 2. Let's write that better, 2, times the 2 on the outside. 2 times 2 is, of course, 4. Now 4 was really log base 2 of 16. Well, think to yourself, how did I get from 2 log base 2 of 4 to just log base 2 of 16? Well, what we did is we got rid of this 2, because we don't have a 2 in the front anymore, but we didn't just get rid of it, we made that 2 an exponent, because 4 squared is indeed 16. So when I'm when I'm adding logarithms, I can multiply. When I'm subtracting logarithms, I can divide. Now here, I'm taking a logarithm and multiplying by a number. Well, now I can turn multiplication into an exponent. Addition becomes multiplication, subtraction becomes division, multiplication becomes an exponent. So, we have 3 properties of logarithms. Technically we have 4, but I'm going to save the 4th one for later. So the first 3 properties of logarithms, the first one is called the product rule. We call it the product rule because when we are multiplying something inside of a logarithm, I can expand that into the sum of the logarithm of the first factor plus the logarithm of the second factor. Multiplication becomes addition. Now notice I just used the word expand because I'm breaking my single logarithm into 2 logarithms. So when we're going this way, we call it expanding. And then the second part of this lesson is going to be about condensing. When I'm going in this direction, I call it condensing. And if I have multiple logarithms, I can condense into a single logarithm. If I have a single logarithm, I can expand into multiple logarithms. Now, a quick little aside about the product rule, just to prove why this rule works. Take any generic logarithm base b of x and add it to any generic logarithm base b of y. Now, if I define each of those logarithms separately, I'm just going to use m and n as the arbitrary definition of those logarithms. So log base b of x is m, log base b of y is n. Now, if m is the log base b of x, what I'm actually saying is b to the m power equals x. Over here, b to the n power equals y, rewriting the logarithm in an exponential form. Now, if I multiply these expressions together, b to the m times b to the n, then I would also be multiplying x by y. Now, again, multiplying like bases really just means add the exponents. So b to the m times b to the n is actually b to the m plus n. And then that exponential expression can be retranslated back into a logarithmic expression. M plus n is the exponent that b must be raised to get xy. Therefore, log base b of xy is m plus n, which of course m was originally log base b of x, and n was originally log base b of y. So what I've done there is I've proven that if I add log base b of x and log base b of y, it will always be log base b of the product x and y. So again, we call that the product rule. The quotient rule basically operates the same way. Just as multiplication becomes addition, division becomes subtraction. That rule is just a corollary to that previous rule. It doesn't require its own separate proof. If you're multiplying and that becomes addition, then division should become subtraction. And the third rule we call the power rule. The power rule just says that if I have an exponent on the interior input value of a logarithm, that exponent can be brought up front as a coefficient. So an exponent becomes multiplication. Proof of that property, consider x to the y as x times x times x times x times x, a y number of times. I don't know how many x's there are. There are exactly y x's, so there's not an infinite number of x's, there's a finite number of x's that are being multiplied together. There's exactly y number of x's that are being multiplied together. Now, using that product rule, that means I can break each of these individual x's into their own logarithms added together. Log of the first x, log of the second x, log of the third x, and so on and so forth until I get to the final x. Again, it's not an infinite number of x's, it's a finite number of x's, but there's exactly y number of them. So if I add them all up, that would really just be log base b of x times y. Therefore, if I have log base b of x to the y, that's going to equal y times log base b of x. The exponent becomes the coefficient. So let's take those three rules and put them into action. Let's start with a few simple examples before we look at some more complex ones. Let's expand log of 2a cubed. Now, the first thing we need to recognize is that 3. Look at that exponent. Look at that 3. That 3 is the exponent on the a. That 3 is not the exponent on the 2. The 2 is not being raised to the 3. It does not say 2 times a. It says 2 times a cubed. That is the most common misunderstanding that we have on this expression here. When I see a number times a variable to a power, that power does not attach to the number, it only attaches to the variable. The exponent comes before multiplication, so it's not 2 times a and then cubed, it's 2 times a cubed, which means we have a multiplication. And anytime I have multiplication inside a logarithm, I can break that into two separate logarithms. Multiplication becomes addition of the logarithms of each factor of that multiplication problem. So log of 2 plus log of a cubed. But we're not done, because log of a cubed can be expanded further. Anytime I have an exponent, I can turn that into a coefficient. That 3 can come up front as the coefficient of log of a. This is now fully expanded, and that would be my answer. I took a single logarithm and broke it into two logarithms. Let's look at another case. In this case, we have division. Now remember, when it comes to division, we're going to separate that into subtraction. But of course, we also still have multiplication. I still see that a times b up here. So we're actually going to have 1, 2, 3 separate logarithms. For each factor of a quantity, you're going to have a separate logarithm. A is a factor, b is a factor, c is a factor. Now, once we've practiced enough of this, my expectation is that you just go straight to the answer in one step. I don't expect to see any scratch work on these types of problems. Just look at the question, write down the answer, move on to the next one. But in the meantime, let's look at the process that this could be expanded. And the idea is recognizing what is grouped together. On the previous example, 2a cubed, the a is being cubed, the 2 is not being cubed. So we have 2 as a group, and we had a cubed as a group. In this case, keep in mind there are invisible parentheses. A fraction on its own is a grouping symbol. So I have logarithm of the group ab over c. But within the fraction, I have a numerator and a denominator. ab is a group and c is a group. So when I break this up, I'm going to start with the outermost group. In this case, The product AB is inside the fraction AB over C. So I'm going to start by breaking up the fraction, log of the top minus log of the bottom. Notice I kept the parentheses around the AB to indicate that that group is still together, yet the C, there's only a single term there. I don't need to group a single term with itself, so I didn't bother putting the parentheses there. Remember, when it comes to parentheses, keep writing them unless you have a good reason not to write them. Don't not write them because you think you don't need them. Write them regardless of whether you think you need them or not. If you know you don't need them, then you can skip writing the parentheses. So I'm going to keep expanding until I'm done. Log of AB, that's a product right there, so I'm going to expand that into addition, log of A plus log of B, but I'm not going to forget that that log of A plus log of B is still part of a bigger problem. Notice I'm going to keep those grouping symbols until I know I don't need them anymore. Log of AB becomes the quantity log of A plus log of B minus log C. Now in this case, if I don't put the parentheses versus if I do put the parentheses, hopefully you'll recognize that it's the same expression either way. Those parentheses don't provide any extra meaning to the problem, so I'm going to go ahead and erase those parentheses. I don't need to put them. So that would be my final answer. Log of A plus log of B minus log of C. Let's do a similar yet different one. Feel free to take a moment to try this one on your own. Play when you're ready. All right, so we're going to break this up just like we did before. I'm going to imagine my invisible parentheses. You don't actually have to write these parentheses. I'm just putting them here to illustrate where those grouping symbols actually are. So when I break this up initially, I'm going to have log of the top minus log of the bottom. I also recognize BC is still a product unto itself, so I can break that up into log of B plus log of C, and I bring down the log of A minus with that problem. Now hopefully immediately when you look at this you recognize there's a problem, because this time if I put the parentheses versus if I don't put the parentheses, those are two very different problems. We've seen this enough times throughout this course. When I'm subtracting a quantity, I absolutely positively need to put the parentheses. If I don't put the parentheses, this is wrong. If I put the parentheses, this is now right. And because I have those parentheses with subtraction on the outside, I can actually distribute that negative, and I get log of A minus log of B minus log of C as my final answer. Now just to take a quick look at those two examples comparatively, this is what I mean, what I meant earlier by feel free to just go to the answer in one step on these problems. The key is recognizing how many logarithms we're breaking this into. I have A, B, and C. I have A, B, and C. So regardless, I'm breaking this into 3 logarithms. But then the only other thing I need to worry about is the logarithm positive or negative? Well, notice this logarithm, log of A, is positive. Log of B is also positive. And log of C is negative. Whereas on this one, both B and C are negative, and log of A is positive. It comes down to, did the factor come from the top, or did it come from the bottom? On log of AB over C, both A and B came from the top, so those logarithms are positive. C came from the bottom, so that logarithm is negative. Versus on the second one, log of A over BC, A came from the top, so it's positive. B and C both came from the bottom, so they're negative. Feel free to use that as a shortcut going forward. If a factor comes from a numerator, that logarithm will be positive. If a factor comes from a denominator, that logarithm will be negative. One more before I give you a challenging one. Go ahead and break this one up. Play when you're ready. All right. This is one of the other cases that we make most of our frequent errors on. So I see the invisible parentheses. The invisible parentheses, again, you don't have to write these parentheses. I'm just illustrating where the parentheses would be. Log of the top minus log of the bottom. I still have a group B plus C on the bottom, but I don't care. I'm done. That's the final answer. Log of A minus log of B plus C. Do not make up your own rules. Do not make up your own rules. The rules are finite. The rules are static. Whatever the rules were yesterday, those are the same rules that you have today. Those are the same rules you have tomorrow. The beautiful thing about algebra is the rules never change. All you have to do is memorize them. Take a moment right now, go back and look at those 3 rules that you wrote down. The power rule, the product rule, the quotient rule. Pause here, play when you come back to it. Look at those 3 rules. Did you look at those 3 rules? Did you see any rule that said log of x plus y equals log of x plus log of y. Because if you did, you wrote it down wrong. That rule does not exist. There is no rule that says that you can take addition from the inside of a logarithm and expand it into the addition of two separate logarithms. It specifically stated log of b plus log of c was log of b times c, not log of b plus c. You cannot distribute an operation. Log of b plus c is log of b plus c. You cannot distribute an operation. Just like you can't distribute a square. B plus c squared is not b squared plus c squared. Square root of b plus c is not square root of b plus square root of c. You cannot distribute an operation. When you have plus or minus inside of a function, when you have plus or minus inside of an operation, you cannot break that into two separate problems. Now, when you have multiplication division, you can break that up, but you cannot break up addition subtraction. When you see logarithm of a sum or logarithm of a difference, you are done. Now let's start looking at some more difficult examples. Feel free to take a moment, try this one on your own, pause here, play when you're ready. Now, first thing I always like to point out on this problem, again, it's those invisible parentheses. We don't always write the parentheses, but you need to recognize where the parentheses would have been. On an example like this, log of 2x, I could actually interpret this two different ways. I could think of this as saying log 2 is the coefficient and x is the variable. Or I can interpret this as log of the expression 2x. Either way, I could interpret this correctly and conclude either one and be correct. But the thing is, on that top one, log of 2 times x, if that's what I wanted to convey, I would have written it like this. I would have put the variable in front in order to avoid that possibility for confusion. Just like we do with radicals. When I have the square root of 2 times x, I don't write the square root of 2 and then the x. I always write x square root of 2 because there's that possibility for confusion that I can anticipate and avoid. So when it's written like this, log of 2x, that probably means that it's log of the quantity 2x. So that's a safe assumption to make. So in this case, it's not log base 5 of 27 as your coefficient and then a to the fourth b squared root of c. It's actually implied to be this. Log base 5 of the product of 27 a to the fourth b and square root of c. And again, recognize product can be expanded. Anytime you see multiplication, we can break that into a logarithm. So this is going to break up into 4 logarithms. Notice it's not 27 a to the fourth times b times root c. It's 27 times a to the fourth times b times root c. That 27 is not part of the a, it's its own separate factor. So I'm going to break this into 4 separate logarithms. All of them should be log base 5 of 27, plus log base 5 of a to the fourth, plus log base 5 of b, plus log base 5 of square root of c. I'm not done until I fully expand, so anywhere I see an exponent, I need to bring that to the front. Notice I brought the a to the fourth, the 4 became the coefficient of log base 5 of a, and for the square root of c, square root really means an exponent of 1/2, so the 1/2 came to the front as well. Now, someone who's not paying close enough attention will say that this is your final answer, but of course it's not, because look at that 27. Fully expanded means anywhere there's an exponent, that exponent needs to come to the front. Look at that 27. I don't see an exponent on that 27, but I see an exponent in that 27. 27 is 3 cubed. I expect you to recognize perfect squares up to 20 squared, perfect cubes up to 5 cubed, and other few special cases. 27 is 3 cubed. I expect you to recognize that, which means we could bring that 3 to the front, and this will be our final answer. Here's another one. Why don't you try this on your own? Hit play when you're ready. All right, we're going to start by breaking the division into subtraction. We have ln of y squared minus ln of the quantity y minus 1. If you don't put the parentheses, that is no longer saying the same thing. On the y squared, the 2 can come to the front, and that's it. Remember, we cannot break up a subtraction problem. ln cannot be distributed onto the y minus 1, so that is the final answer. Here's a more challenging one. Feel free to pause here, play when you're ready. All right, so what makes this one more challenging is the extra exponents within exponents. Now, keep in mind, we did a whole unit on exponent properties, so my suggestion is ignore the logarithm for a moment and let's just clean this up. y cubed over 2x raised to the fifth. I'm going to take a moment and use my exponent properties to clean this up before I use my log properties to expand the logarithm. So initially, a fraction raised to a power is really a power of the top and power of the bottom separately. So I have y cubed to the fifth and I have 2x to the fifth. On the top, a power to a power is a product, so that will end up being y to the 15th. And on the bottom, 2x to the fifth, remember that's 2 to the fifth and x to the fifth. The power of a product is really a product of powers. Now, of course, 2 to the fifth is 32, but I'm going to leave it as 2 to the fifth because the overall goal here is to expand, and I need to keep in mind that that exponent is 5 is eventually going to be brought to the front. So now, let's expand this. Notice I have y, x, and 2, so I'm going to have 3 logarithms, y to the 15th, 2 to the 5th, and x to the 5th, as representing the interiors of my 3 logarithms. Remember the other rule that we had about the tops are positive, the bottoms are negative, so y will be a positive logarithm, whereas 2 and x will be negative logarithms. And then anywhere I have an exponent, that can come to the front, but before I do that, I'm going to notice, hey, log base 2 of 2, that's actually going to go away completely. When I bring that 5 to the front, it's going to be on its own. Really, that would be 5 times 1. I just didn't bother writing the times 1. Final answer. Now, just for kicks, let's look at that same problem another way. I prefer what I just did. I prefer simplifying the interior and then expanding it from there. But not uncommon for students to look at this the first time and see another route which is absolutely correct. Just because I prefer a route doesn't mean it's the only route to go. When it comes to log and exponent properties, there are often several correct routes to an answer. Through practice, you gain an intuition and you gain a preference for how you want to do these problems. So what some students see when they look at this is they look at that 5 and say, hey, wait a second, can't I just pull that 5 to the front? You sure can. That's using the power rule for logarithms, that 5 can be brought to the front as a coefficient, and then we can essentially just expand the rest of this and keep in mind that 5 is the coefficient of that entire expansion. So expanding this out, y cubed, 2, and x become log base 2 of y cubed, log base 2 of 2, and log base 2 of x. The 2 and the x are negative, the y cubed is positive, but remember this whole thing is being multiplied by 5, so I'll put the whole thing in parentheses with a 5 up front. Then from here I'll keep expanding. Also note log base 2 of 2, that's going to end up being 1, which apparently I took a while to go ahead and replace. And then distributing the 5 gives me 15, 5, and 5 as my coefficients, and here we go. Finally evaluated log base 2 of 2 to be 1. And notice we got the same answer here as we got on the previous slide, 15 log base 2 of y minus 5 log base 2 of x. It's a personal preference which technique you want to use. Do you want to simplify the exponents first and then expand, or do you want to pull off outer layers and then expand as you go? Again, I prefer simplifying everything before you expand because if you don't, you sometimes find that you're having to jump back and forth between techniques. Here are 2 more problems. Pause here, play when you're ready. All right, let's look at one at a time. Again, I prefer to simplify things before I expand. I'm going to recognize that cube root applies to both the 2 and the w to the 5th, which of course implies that I also recognize that that does not say 2w to the 5th. It says 2 times w to the 5th. So what I'm going to do before I even start is I'm going to rewrite this, applying that cube root to each of the 2 and the w separately, and rewriting it as an exponent. It's 2 to the 1/3 and w to the 5/3. So then when I expand, I'm going to break this into 3 logarithms, log of the top, and then minus each of the logs on the bottom, 2 to the 1/3, w to the 5/3. The 1/3 and the 5/3 will come to the front as coefficients, and log of 1 is 0, so that one will go away completely. Final answer. Again, this was not the only route that you could have taken. This is just my preferred route. Looking at the other one, again, I prefer to simplify the expression before I expand it. That square root applies to everything, so I'm going to apply that square root to every individual factor within that expression. Square root of 5 is 5 to the 1/2. X to the 4th gets raised to the 1/2, y gets raised to the 1/2, and then 2w plus 3 squared gets raised to the 1/2. Again, before I expand, I'm going to clean this up a little bit. 5 to the 1/2 and y to the 1/2 can't be cleaned up at all. But x to the 4th to the 1/2, power to a power is a product. 4 times 1/2, that would end up being x squared. And on the bottom, 2w plus 3 squared to the 1/2 is actually just 2w plus 3. I don't know about you, but I much prefer this expression to this expression. I think it's going to be a lot easier to expand this than to expand that original version. So when I expand it, I'm going to break it into 4 separate logarithms. 5x, y, and 2w plus 3 each represent their own logarithms. And then any of the exponents come to the front. Take one quick more extra look. Is there anything else I can simplify? Doesn't look like it. Final answer.